In this video, we're going to discuss something called the student t-distribution. And we use the student t-distribution anytime that we're performing inference for a single mean or two means, and we don't know the population standard deviation. In that instance, we use the sample standard deviation as a point estimator for that unknown population standard deviation. And in conjunction with that, we use this new curve called the student t-distribution. So let's take a look at a couple of properties of the student t-distribution. The first thing you should know is that the graph of the student t-distribution is very similar to the standard normal curve. So we know the standard normal curve is bell-shaped. The student t-distribution is also bell-shaped. Also similar to the standard normal curve, the mean for the t-distribution is 0, and the distribution is symmetric about that mean. One important difference is that the t-distribution has more area or more probability in its tails than the standard normal distribution does. And that's because the t-distribution has a greater spread. So the student t-distribution is wider than the standard normal curve, meaning that using the student t-distribution for our critical value is going to produce larger or wider intervals. Another important difference between the standard normal curve and the student t-distribution is that the exact shape of the t-distribution depends on a quantity called the degrees of freedom. And for cases of a single mean, like we're looking at in our section on confidence intervals, the degrees of freedom, or df, is equal to the sample size minus 1. As that degrees of freedom increases, so as our sample size gets bigger, the graph of the student t-distribution becomes a lot more like the graph of the standard normal curve. And you can see here in this picture, we have this lowest graph, which is really wide and kind of flat, corresponds with a very small sample size. Degrees of freedom of 5 would be n equals 6. That's a very small sample. The next graph up, the middle one here, that's a little less dark, is taller and a little less flat, a little skinnier. That comes from a degrees of freedom, or 13, which would be a sample size of 14. And then we see at the top what we know as the standard normal curve, which is much narrower. They all have a bell shape. They're all symmetric about 0, but the standard normal curve is much narrower than the student t. You will see a note down here that the standard normal curve and the t-distribution with an infinite degrees of freedom are right on top of each other. So as our sample size increases without bound, the t-distribution approaches the standard normal distribution. So with large enough samples, we might as well use the normal distribution. Before calculators were ubiquitous and before they had a stats button on them, often what statisticians would do is that they would only use the student t-distribution for small sample cases, samples under size 30. And once you hit samples of 30 or larger, the student t-distribution was close enough to our standard normal curve that statisticians would just use the tables for the standard normal curve. Now that we have calculators and we can have a computer do that calculation instantaneously for us, it's good practice to use the standard normal curve when we know the standard deviation for the population, and then use the student t if we don't know the standard deviation for the population, regardless of sample size. Last little side note, we can do the same things with the student t-distribution that we did for the normal and standard normal curves during our unit on probability, meaning I can calculate area under the curve, or probability, for a t-distribution, and I can calculate t-scores given a probability or percentage the same way that I did for the standard normal distribution. I press second vars on my calculator to open the distribution menu, and I can see that there's an inverse t, which will get me t-scores given a percentage, and a t-CDF, which will give me a percentage given a t-score. We're primarily going to be focused on the inverse t command because we're going to be using that to find our critical values, just like we did inverse norm for critical values when sigma was known. All right, if you have any questions on anything in the video, feel free to send me an email or drop by office hours. Otherwise, I'll see you in our next video.